this thing to see when it will show up. So here we are, guys. Welcome back. And let's go ahead and finish the last thing we talked about. What I think of as the crown jewel of the trigonometry class, which is trying to find roots of complex numbers using everything else we've done. I mean, this has got it all. It's got the sines and cosines, it's got the trig functions, right? It's got the polar form, so you can see this happening on the circle. It has the symmetries, it has the polynomial, it has rational functions in it, because we're looking at like powers, like simple polynomials like z to the fifth minus 1. Okay, so let's take a look. There's two things we're talking about roots. We generally look at roots of unity. These are roots of unity, okay? And by roots of unity, do you understand what I'm saying on that? This is called 1, also called unity, okay? And the solutions right here, these are then roots of unity. That's where the language comes from, okay? And it's still a polynomial expression. You're solving z to the n equals some power, and you're going to find the different z values. With any polynomial of degree n, oh, I need to get my chat back, making sure so I don't miss any questions or comments. Okay. Okay. Yeah. Now, if Access students, I've got an email from my Access person about something or other, and I'm going to have to escalate that to them. If I have issues, if any Access students, man, my papers are all over the place. Please email me if you're an Access student, and I will escalate anything that I need to escalate to them. Okay, and as far as, yeah, Access students, if I have any Access students, obviously they are going to have a chance to have, mostly that ends up being extended time, so they get extended time to submit the final, I guess. But I'm going to talk to people about that and see how that works, okay? So in any case, if you're an Access student, please email me and I'll work from there. I didn't really want that to be recorded. Oh well. I think I cut it before I put it up on YouTube. Okay. So anyway, so this is what we're looking at. You're going to end up with n solutions. And the n solutions are really easy to see for unity because you just take multiples of 360 divided by n, or 2 pi divided by n if you're doing it in radians. I'm doing it here in degrees because those are easy to figure out. So the idea is here, I'm looking at unity, and I think of unity, I start out thinking of it as just the 1 there on the complex plane, right? If I'm looking at the 1 on the complex plane, that's this point, which is cis 0, or cis 360 degrees, because these things are periodic, right? And this is the one that I'm going to use for my solutions. I'm going to divide that by 5, because if I divide 0 by 5, I don't have anything to work with. What's 360 divided by 5? Anybody? Go type it in the chat. What's 360 divided by 5? I'm not moving until I see that number showing up in the chat. What's 360 degrees divided by 5? Yeah, there we go. Okay, well, it's close. You might want to use a calculator, Andres. Yeah. That's actually 360 divided by 6, Andres. And that would be great if I was working with working with the 6th roots of unity, but now I'm looking with the 5th root of unity. There we go. Everybody sees that. That's great. Okay, that's cool. So this is what we're looking at here. We're looking at cis. This is cosine plus I sine of 72 degrees, right? And now for the other roots, we just start multiplying. Or if you like, just add 72 again and again. So twice that is cis 144 degrees, right? Cis again means cosine plus I sine. Okay, and again, let me kind of do that on the side over here. cosine theta plus I sine theta. And nobody wants to write all that, so they write cis theta. And remember, this is a complex number. Okay, so that's where that's at. Okay, and somebody's out there ready to rock and roll. Yes, the next one's gonna be 216. And let me freeze my screen a little bit. There we go. And so this is gonna be the cis of 216. Now add 72 again. What do we get? What do we get when we add 72 again? 288. That's right. And now add 72 one more time. What do you get? And you see what happened? We're right back to where we're at. 360 degrees. And this is what happens as you work with it right there. This is the same thing as cis 0. And, whoop, didn't mean to do that. There we go. This is the same thing as cis 0. Dang, keep on. I'm reaching with the erase key and I hit the frame key. There we go. Because I wrote 0 looking like a theta. There we go. Cis 0, which is also known as just 1, right? Now you notice we ended up right back at 1. And looking at the original equation, right? You know that 1 was a root, right? 1 was a solution because 1 to the 5th equals 1. Yeah? Okay. And so that's really the first solution, but it comes before all the other solutions. And so I like to think of that as Z0. And this is fairly standard. I'm calling this like the 5th solution, Z sub 1. There's 5 solutions, Z sub 1, 2, 3, 4, and 5. But the 5th one is actually the first solution, or the before the first solution. It's the initial solution. And between them all right there, these 5, you get it all. But now I want you to see where these solutions map out. And this is what they look like, okay? These are spokes on a wheel. Spokes on a wheel. And they're nice and evenly distributed around the circle and equal distance apart. And that's if we're dealing with the roots of 1. The difference is if we're looking at the roots of anything else, well, they're still going to be equally distributed, but they might be shifted around a little bit. That's kind of where we're going. And let me show you, that's the answer. Let me show you the question, the Jeopardy thing. Now let's say that we're not trying to find the roots of 1. We're looking for the roots of any generic complex number W. And this is still a polynomial. It's z to the n equals w, and it's going to have n roots. And the way to solve it is to immediately change w into its polar form. Then when it's in its polar form, you can take the roots of this. I want the root of this. I want the square, the 1 over n power. That's the root of this. And there's going to be n solutions, right? But the first one is going to be really easy. You're going to start off just finding this is the r. You're going to take the nth root of r. So you're the square root or the cube root. The last one, I want the 5th root. In the example I'm about to show you, I'm going to want the cube root of r. And then I'm going to find a first solution. Okay? I'm going to find a first solution. And the first solution is going to come just from dividing the angle by the power. And all the other solutions are going to come from adding in roots of unity, or multiplying this thing by the roots of unity. And that's going to give me all the powers that I'm looking for. Okay? Because the idea is when I multiply 3, the 360 goes away when I finish multiplying it out. I'll show you what I'm saying on this in a second. So anyway, so let's take a look at this example. and take it apart, okay? So the first thing is, I'm assuming z cubed is equal to 8i. The first thing you notice is n is equal to 3, right? But now let's zoom in a little bit further. I'm saying that 8i is 8 cis 90 degrees. 8 cis 90 degrees. How do I know that? This one's actually very easy to see, okay? Imagine you're trying to graph 8i. In the complex plane. Here it is, right? Yeah. What's the angle? What's the angle? Anybody? Because you always measure from the positive real axis, right? What's the angle? Well, the angle here, what's this angle? From here, the real axis, to, yeah. Do you see it's 90? Danny sees it's 90. 8i right there is just straight up on the imaginary axis, and you can see it's 90 degrees, right? Now, how far is it from the origin? How far is 8i from the origin? Anybody? Yeah, it's 8 units from the origin. I mean, I could do it if it was like not directly on an axis. It'd be x squared plus y squared and the square root, right? In this case, the real part is 0, the imaginary part is 8. So, but I kept this like really, really easy so that we could see it. And the idea here is the distance from the origin is 8, and the angle from the positive real axis, which is normally the positive x-axis, is 90 degrees. And that translates to 890 degrees in polar coordinates. But for calculation's sake, we use the cis form of the calculation. This is 8 times the cosine of 90 degrees. What's the cosine of 90 degrees? What's the cosine of 90 degrees, guys? I'll give you a hint. Yeah, exactly. Thank you. Plus I times the sine of 90 degrees. What's the sine of 90 degrees? Anybody? 1. So you see, this is 8 times 0 plus I times 1, all of it times 8, right? 8 times 0 plus 8 times I times 1, right? And so it's just 8I. This is really easy, right? So this is the coordinates, right? 0, 8 in the complex plane, right? And so the radius is 8, and the angle is 90 degrees. And I picked one that was really easy to pick out the angle from. And I also picked a cube for 8 so that we could numbers really easy. Okay? Ryan, you got a question or anything like that? You can go ahead and just put it in the chat. That's where I'm following things. Okay? Yeah. And so there, we're always going to find the first solution really, really easy. You take the cube root, or the 4th root, or the 5th root, or whatever, and that's going to, well, how the radius is going to change. Okay? And then I'm just going to divide by 3 to find the first solution. Now you can check this one, right? You can check this. Because what's 2 cubed? Well, let's do it this way. 2 cis 30 cubed is going to be 2 cubed, yes, times cis 30 cubed. And now by de Moivre or Euler, the cube on the cis is just multiply. Because remember, cis, that angle, is an exponent. e to the I theta, or in this case, e to the I 30 degrees, and I'm cubing that. And that's where you get 8 cis 9. Okay, and that's how it is. So that was just kind of proving the fact that this works. Why see Jada in here? Yeah, Jada, please answer the poll. Please answer the poll. I want to make sure that okay, so you're on your phone, so we didn't get a computer for you. And I'm listening. I was talking to Alex before the class today, and he said he was going to be able to pick up a laptop at Kendall today. So I don't know if we're still going to have laptops or whatever like that available. Yeah. Da, da, da. Write me and let me see if I can get. But you were like a student worker. You should have been able. You should have had like first dibs. Write me right there, and so I can follow up and see if we can take care of your issues too. Okay? Because you shouldn't be stuck on a phone. All right. Anyway, so that's how that works. I'm going to erase this again because it's like all in the way. Okay? But the idea is fairly straightforward, okay? Once you've seen it, you can't unsee it. There we go. So the basic rule here, as we're doing this, is if you want to find the first one, looking at the cube, trying to find the cube root then. You take the cube root of r, and then you divide the angle by 3, because we're taking the 1 power with an exponent, and so you multiply by 1/3. So remember, this is just a number, and this is an exponent. And so when you take the cube root of a product, it's the product of the cube roots. Cube root of 2, cube root of 8 is 2, and the cube root of cis 90, cube root of e to the I 90 degrees, is e to the I 30 degrees, which is cis 30. That's how it works. Now for everything else, for the rest of the solutions, we're going to start adding in thirds of 360. Okay? So for Z1, I'm adding 1/3 of 360, 120. And for Z2, I'm adding in 2/3 of 360, or 240. But you get this just by finding a first solution, adding in 1/3, adding in another third. If you added another third in, another 120, you'd find yourself right back to where we started at Z0, because we'll end up with 390, right? And 390 is the same thing as 30 because of periodicity. And again, so there's the pretty picture on the side here, and that's the slide that's going to show up on Blackboard. All right, now with that underway, these are the basic how you do it. At this point, I want to launch into a review of trigonometry, because that's the exam you guys are going to get on Friday. All right, so let's look at a review. The first thing we started the very first day when we were looking at trigonometry is we looked at, I cut to the chase and told you about the whole cosine theta, sine theta, right? And how that sits on the side of the unit circle. Those are the coordinates of the unit circle. I want you to notice, first of all, how nicely that first day, when I told you you find any point on the unit circle, cosine theta, sine theta, this just maps perfectly to the idea of cis theta on the complex plane. So in the very first presentation when I showed this to you, I wanted to get you guys to the point where you'd be able to see immediately from the things that you've seen before that we're going to be looking at cis theta. Okay? because in the complex plane, this is just cosine theta plus I sine theta. Okay, and that was the first thing we want to look at. Now, basic measurements that we came up with here were arc length and area, and those you had to know, right? And we also looked at like angular speed and stuff like that. But let's go ahead and take a look at this right now, okay? And there's some basic formulas that you need to remember. One of the things is that, well, the arc length, S, is just the angle in radians, theta, times a scale factor, and the scale factor is just the radius, r theta. And that was our first introduction to polar form, because then we're looking at what? R theta, that's where we're going for polar form, r's and thetas, right? And then we went ahead and integrated that, except we didn't call it integration. And we won't call it integration until like end of Calc 1, beginning of Calc 2. But the idea is pretty simple. You raise the power on r, okay? And then you divide by that raised power. R to the first becomes r to the second, and divide by 2 times theta. And that ends up getting written all the time as 1/2 r squared theta. But what's happened here is that the theta stayed the same. We actually just integrated r and got the area from the arc length. All right, so again, you don't worry about what it means to be integrated or anything like that. We'll formal definitions in calculus, but the basics are very simple for anything polynomial. Okay, now, what was the next thing we looked at here? The next thing we looked at were trig graphs, right? Now, I actually brought students to the board so we could do this right. Yeah. The one that you always want to be able to do, first of all, is sine, right? Sine is your most basic trig graph, right? Remember how we started sine? What's the sine of 0, guys? What's the sine of 0? Anybody? What's the sine of 0? Yeah, 0, 0, 0, 0. There we go. Thank you, Winner. Thank you, Felix. Thank you, Danny. Yeah, y'all can fill this in. You know, just jam up that chat. That's fine. Yeah. Sweet, sweet, sweet. Yeah. Okay, so that's very simple. And so sine is like the first thing that you always learn, right? Sine of 0 is 0. And what we're going to do is we're going to cut this off into some particular length, cut that length in half, and cut those lengths in half. And we're going to call this 2 pi or 360. Okay, and then we're going to cut those lengths in half and half. Half of 2 pi is pi, that's 180 degrees. And half of pi is pi over 2. So I got 1/2, 2 halves, 3 halves, and 4 halves of pi. And that gives me a basic sketches. I could go back the other side too, at -1/2 and -1 pi's, right? Now for graphing this, the sines and cosines, remember it's just up 1, down 1 stuff, right? If I'm starting at 0 and moving to the right, I'm going to go up 1, yeah? At the first check mark. That's all there is to it on the basic sine graph, right? And then it's going to be down 1, because that's as high as you can go, right? So it's down 1 and then down 1 again. And I made you guys do this. So it's very simple, right? You start out at 0, and then it's up 1 until you get to 1, and then down 1, and that's as far down as you can go, so you got to come up 1. Coming backwards, I go down 1, and that's as far as I can go, then come up 1. And that's the basic scaffold for building your sine graph. And from here, you can just kind of like sketch it as you want. I want to be concave down on this top half. If I had this thing all perfectly to scale, I'd be running through that axis right here at a slope of -1. But I'm not perfectly to scale. And then sketch it the rest of the way. So this basics on the sine graph, everyone is going to want you to know. Your physics people are going to want to know this. All your engineering people are going to want to know this. Everyone wants you to at least know the sine graph. You can't do electricity without sine graphs, because every time you plug in your toaster or whatever, you're going into something that has a voltage that's following this curve. I know we talk about 120 volts, but that 120 volts is actually RMS, root mean square. They average this out over time, and they talk about the root mean square of 120 degrees. And you'll worry about that later. But the actual voltage underneath that root mean square is following the sine curve. You don't notice it quite so much because it's happening 60 times a second. That's the usual household current, is 60 hertz at 120 volts. Okay. And 3-phase to even it out. All right, so that's the basics, yeah? Now, but we also want to talk about amplitude, period, and phase shift, yeah? Amplitude, well, all that does is stretch this thing up and down, right? Period, well, period has to do with the angular speed, omega, right? And in particular, I'm going to draw another curve over here on the side. Okay. Oh, missed. There we go. So let's talk about 5. No, here we go. Let's do this example this time. We're going to do 5 tan 3x plus pi over 3. Okay? This is a fairly simple one. On this one, what's the amplitude, guys? Somebody tell me what the amplitude is. Yay! Jada got it. Yeah, this is the amplitude. And for this, you kind of, because it's tangent, I'm going to pick a point right there. Where I would normally put 1, I put 5. And that's not a point on the curve. So I don't want to show it as a dot. That's just a hash mark at 5. Okay? Now, what is, and again, this is A is 5, right? That's the amplitude. Now, what's the angular speed here? What's omega? What's the omega here, guys? Somebody tell me what omega is. Somebody tell me what omega is. We've done this before. Somebody tell me what omega is. What is my solution multiplier? What is my angular speed? What is the first number that you see? It's omega. What is it? 3. Yay, 3. There's omega. It's 3. Okay? Now, given omega, we know the period now, right? What's the period? The period, we had a formula for this, right? It's, what, 2 pi over omega, right? 2 pi over omega. How many people think it's 2 pi over omega? Everybody put your hand up if you think it's 2 pi over omega. If you think it's 2 pi over omega, put your hand up. Okay, you can stop now. You can stop now. Okay, because that was Professor being tricksy. Now, everybody who thinks it's pi over omega, put your hand up now. Oh, look, Professor's got his hand up. Normally, it's 2 pi over omega. This is tangent. And tangent and cotangent work with pi over omega. And because tangent and cotangent have period 2, have period pi, have a natural period of pi. Everything else has a natural period of 2 pi, and that's why that works, okay? So in this case, my period is pi over 3, yeah? My period is pi over 3. Now, the next fun question for everybody, what's the phase shift? Now, does anybody remember how to calculate the phase shift? It's really easy. It's really, really easy. As soon as you remember it, you won't forget it. How do you calculate the phase shift? Anybody? You can speak if you want. Yeah. Who? Jada, how do I calculate the phase shift?
You have to solve, like you make the equation equal to 0.
Yes, that's exactly. Girl, you just made me so happy. Yes, that's exactly how you do it. It's 3x plus pi over 3 equals 0. Solve that for x. That's all there is to it. Right? So x is my phase shift when I set this equal to 0. And it's going to be what? Negative pi over 9, right? Yeah? Okay. And that's all there is to it. Now here's what I'm going to do. I'm going to do something kind of tricksy, because I can't just shift this off. It's really, I mean, you can do it with other tools, and it works okay. But I'm going to be doing something here. I'm going to get my usual 4 hash marks, okay? I'm going to cut them in half, cut them in half, cut them in half, right? Okay. And now this is normally, the y-axis is normally my x equals 0 axis. And I'm going to set up origin now at negative pi over 9. Okay? And do I want to do it that way? Oh, no, I don't want to do it that way. I'm just going to graph the tangent function in the usual way, okay? So the tangent function, you remember, starts at 0, yeah? Okay? And then it comes up to the 5, and then it blows up, yeah? This is always increasing, right? And then it blows down, comes back up, and comes through here. And to have a nice graph on this, we use this as my okay, so this is always increasing and always decreasing. Always increasing and always decreasing for cotangent. The tangent's always increasing. Okay? And let's duplicate that over here. Okay? And so now the way I set this up, my period was pi over 3, yeah? Okay. And so it's a little awkward. Let me clean that up. My period was pi over 3. There we go. That's much bigger. Okay. My period was pi over 3, and here's one full period. okay? And half of that is pi over 6, and half of that is pi over 12, okay? And if I'm doing this right, pi over 6 plus pi over 12 is 1/12, 2/12, 3/12. 3/12 is pi over 4, yeah? And so there's my basic hash marks on this. Now you see my saying plus, this is my cheat. I'm starting here at negative pi over 9. And all of these are plus negative pi over 9. Which is awkward. So this is 1/12 minus 1/9 pi. This is 1/6 minus 1/9 pi. This is 1/4 minus 1/9 pi. I know it's much nicer. This is 1/3 minus 1 pi. That's the actual things. And so that's not actually a y-axis. This is an x equals negative pi over 9 axis. But it gives you the idea on how this works right there. We can still see the period off of this, and we can see the phase shift. And you can calculate the phase shift and the period. I would not normally do a shifted thing like this on an exam because it gets really nasty looking. But I wanted you to see what the basics are. I can certainly ask you to calculate phase shift and period. And I want you to be able to obviously read the amplitude and the angular speed, omega, off of this. That's immediate. And then after that, you have to calculate the period and the phase shift. But that's where that was at. So that was the basics on graphing these things. The other thing I wanted to make sure that you guys understood was things that are just basics that I want you to know, right? And one of those basics that I want you to know are the principal angles, yes? The principal grid, yeah? And for that, we have theta, sine theta, cosine theta, and tangent theta, right? And these are the principal angles. You think of as 30 degrees, wait, start with 0. You start at 0, and then 30 degrees, 45 degrees. Notice we've only gone up 15 there, right? And then 6, 90, right? The 30, 45, and 60 are really close together. And then there's 30-degree gap between the first and last, right? Okay. I think of these as 0, and then pi over 6. Whoa, lost my thing. 4, 3, 2. Okay. And for these, the very least you need to know, and that's really all you need to know, is just the sign. What's the sign of 0, everybody? Sign of 0? Yep, Jade is fast. That's always your benchmark, guys. And you'll find yourself, especially in calculus, you get all kinds of confused. Remember, that's your benchmark. You'll be taking derivatives and all that from sine. It's the first thing you'll be doing as soon as you start taking derivatives. And the thing you want to always remember is the sign of 0 is 0. Okay, yeah. And so the next thing, yeah, this is the principal angles, right? And this one I have a phrase for you, right? The first step, you're how far? First step, you're how far? The first step, you're, well, on the principal angles, Brian. First step, you're how far? Anybody? It rhymes with chicken and a prayer. First step, you're halfway there. First step, you're halfway there. And that's how you remember it. You're halfway in the first step. See? And everything else goes, then you get the root 2 over 2, and then the root 3 over 2. And then you get to 1. Okay? So you remember, the sign of 0 is 0, And then the first step, you're halfway there. And that's enough to do it, right? Now for the cosine, how do I find the cosines from the sines? Anybody? Flip it. Exactly, Danny. Yeah. So this was like really easy, yeah? And the first step, you're halfway there. You notice at 45 degrees, the sine and the cosine are the same, because the x and y coordinates are always going to be the same at a 45-degree angle, right? Yeah. And then root 3 over 2 and 1. And then for the tangent, you just use the identities, tangent sine over cosine. 0 divided by 1 is 0. 1/2 over root 3 halves is 1 over root 3. And 1, just because they're the same, root 3 halves over 1 is root 3. And then you can't divide by 0, so it's undefined. That's the basics. And that is so basic, I'm going to assume that everybody knows it. So I just wrote about it, but I'm going to take that off the slide. Okay? Because once you've seen it, a little reminder, you'll never forget it. Okay, so that's the basic stuff. Knowing what the sine graph looks like, knowing that the cosine and sine show up as coordinates on the unit circle, which also translates to the complex plane. The basic formulas for arc length and area, yeah, from angular speed is, I'm not going to worry about just now. But yeah, the angular speed that you come off of that shows up in these amplitude and speed, phase shift, and period calculations. And so it's important to be able to recognize them. Okay. So I got Alex. I ended up with 19 guys, right? I'm still missing 4. Well, it's bugging me that I can't tell which 4 I'm missing. But hey, I got 19 students in here now. That's good. 20 students now. Oh, somebody must have popped out. So I'm missing 3, and it really bugs me not knowing which 3 it is. But I'll know from the report. I don't want to have people list missing. Yeah. Okay. So now let's talk about undoing the Triggs, right? And we're talking about inverse Triggs now, right? And for inverse Triggs, it's important to remember that you don't get all 360 degrees, right? Amongst the thing of the inverse Triggs, one of the things you notice right there is your calculator will never give an answer in quadri. Your calculator for arc sine, arc cosine, arc tangent, those are the only buttons you have in your calculator, only give answers in quadrants 1 and 2 and 4. Okay? And it depends upon whether the original function was an x thing or a y thing. Cosine is an x thing, yeah? So for cosine, I know the arc cosine, because cosine is an x thing, I know my arc cosine is going to follow values on x, and x values on the top half plane run through first quadrant and second quadrant. Similarly, the sine and the tangent, this arc sine is a y thing, and so its values are going to return in the first and fourth quadrants for the arc sine. Okay? And the tangent comes along with it. Now, also remember the ones that are missing, right? What's the inverse of sine is cosecant, yes? So if I'm trying to find the arc cosecant of something, I take that as the arc sine of its reciprocal, right? For example, if I want the arc secant, that's another one that you don't have in your calculator. You got these 3 and you don't have the other 3, right? Arc secant of x, I'm asked to find the arcsecant of x. I can find that using the arc cosine button of 1 over x. So you just reciprocate, right? So I'm looking for the arcsecant of 2. Instead, I'll find the arc cosine of 1/2. Because we just did the grid, everybody remembers that was first step halfway there back from 90 degrees, bring it to 60 degrees. Or as I think of it as pi over 3. Okay. Now, let's take a really simple example to run us through on this, okay? Sine of the arctangent of x. Okay, guys. So this will take us through, and I'm going to find a closed form for the sine of the arctangent of x. Now, everybody tell me, what am I looking for? Am I looking for an angle or a ratio? Am I looking for an angle or a ratio? Somebody's got to tell me. Hint, look at the outside. Hint. Nope, that's an angle. What's that? Ratio, okay? Look at the outside when you're looking at these, okay? And so there we are. That's a ratio. Now, if you're trying to draw a ratio, trying to find a ratio, what are we going to draw, guys? Triangle or circle? Yay! We're going to find it. We're going to draw a triangle. Now, a triangle is going to have an angle. You know what angle that is? You know what angle it is? That's this angle. That's the arctangent of x. And that's how we label this in. No, it's not 90 degrees. It's not 90 degrees. It's just whatever the arctangent of x is. It's just whatever the arctangent of x is. Okay? Now, if I say that theta is the arctangent of x, that's really enough. I see x over 1, I can just go for it. But here's how this works, okay? We're going to take the tangent of both sides. I mean, yes, this comes out, yes, x over 1. Everybody, the people clever out there, yes, x over 1, that's where you go, okay? But this is what's going to happen. We take the tangent of theta, and we set that equal to the tangent of the arctangent of x. The idea being that the tangent and the arctangent cancel as compositions. Okay? And this means that we end up saying that the tangent of theta is x. But you could have seen that originally. I just looked at the x here, and that was enough to see that I was at, for my triangle, I had an opposite side of x and an adjacent side of 1. And that's enough to be able to find the hypotenuse, right? So, the hypotenuse is bigger or smaller, guys? It's bigger or smaller than a leg? Bigger. That means add the squares. Okay? That's just your basic thing. If I'm looking for a leg, I'll subtract squares. But if I'm looking for hypotenuse, I'm going to add squares and then take the square root, right? And now we have all three sides. Okay, so sine is what? Sine is adjacent over hypotenuse, what? Opposite or adjacent over hypotenuse? Anybody? Yep, yep. Actually, O over H, but yeah, that's okay. That's cool. Yeah, and so there it is. And now you can just read off the sign, yeah? The sine of the arctangent of x is obviously written as opposite over hypotenuse. And that was a closed form that used a lot of just about everything that we needed to know on this. First of all, I knew that I had to draw a triangle because I'm looking for sine, a ratio. I had the arctangent, so this tells me something about, I was looking at the theta as the arctangent of x, and that told me that I had to use the inverse function tangent applied to that argument tangent theta in order to figure out what x was, what the tangent was, and then turn that into ratio and fill in the triangle, and there we were, right? Okay. So that was the basics on how to work that. We did other things, but that's okay, right? That's the basics. Now, yeah, and also with the circles as well, but this was just a review, right? Okay. Now, we also looked at identities, right? Now, the identities, I can break them into three types: the basic grid identities, the Pythagorean identities, and the Eulerian identities. These are the things I got from the Euler thing. Now, you get the basic grid identities just by looking at the grid, yeah? Sine, let me freeze this in, and look at the grid identities. Sine, cosine, tangent. Okay? On the other side, we're going to get the reciprocals, yes? On the other side, we get the reciprocals, and the reciprocals, 1 over sine is what, guys? 1 over sine is what? What's the reciprocal of the sine function? Cosecant. That's right, milady. Cosecant, yes? And that's everything you need to know, right? Because the other one has to be secant. And the only thing that's missing is the cotangent, which is at the same time, reciprocal and a cofunction. It's the only one that does that, right? So we get function and 1 over function. That's the reciprocal identities, yeah? We also, from the grid and just from the names, we get the cofunction identities, right? The sine of x is the cosine of 90 minus x, or pi over 2 minus x, the way I think of it, right? And because they're cofunctions, and co stands for complementary, angles. Because the thing to remember is that cofunction means complementary function, or the function of the complementary angle. That's how those work, right? Okay. Also from the grid, evens. Okay. And then the basic sine over cosine is tangent, cosecant over secant is cotangent, which are almost too boring to write, yeah? Okay. The Pythagorean theorem identities are a whole lot easier, right? Are just the ones that you know, right? This is not what I'm trying to do. This is what I'm trying to do. Okay. The Pythagorean identities all come from sine and cosine, right? Sine squared plus sine squared equals 1. And this gives you the other two just by dividing by cosine squared. One over cosine is secant, so that's secant squared. Or dividing by the original one by the sine squared. And those are all the Pythagorean identities, okay? Of these, the first two are the most important, and I'll just write their usual way that you'll see them. Sine squared is 1 minus cosine squared, or tan squared is sec squared minus 1. Those are the two most important ways of seeing these, because that will come up when we do trig substitutions in Calc 2. That's the ones that you're supposed to be especially interested in. And yeah, all this stuff is going to show up. I'm especially interested in making sure that you have all the trig that you need for calculus. Okay, hence the name, pre-calculus, right? Now the Euler identities, I'm going to handle those in a different page. Here we go. And the Eulerian identities are going to come from the Euler ID. And remember, the Euler ID settle this down, is given by e to the I theta is cis theta. Okay, which I then abstract out as c plus is for theta, which I can then multiply by c plus is for phi. And that's how you guys want to do this. I mean, yes, you can memorize the sum and difference formulas and all that, but it's just better to go from c plus I to c plus is. And if you do this, you will end up with c. If theta and phi are the same, then it's just cosine squared. But if they're different, it's cosine theta, cosine phi. And you get plus ICS plus ISC minus SS. Where the minus comes from, let me actually just write that in. Plus I squared SS. That's where the minus comes from. And then the real part is cosine. And the imaginary part is sine. Dang, I keep on punching the wrong button. There we go. Okay. And so there, now we can write the two identities very quickly. The cosine of theta plus phi, yeah, is cos minus sine. And the sine of theta plus phi, reverse these. You really want to look at this the other direction, because I want to end with s. I really want to end with s, because when we plug in negative phi, not negative theta, and negative phi is going to change the sign in that last term. So sine theta cos phi plus cs cos theta sine phi. And I wanted to end with s because these change sign. These change sign when you go from phi to negative phi. to get yourself the difference formulas. And again, I don't want you to memorize the sum and difference formulas separately. I want you to memorize just this one and then plug in negative phi. Okay? Now, so what that comes down to is if you're trying to look for, if you want just the real brief way to actually write this so that you can memorize it, if you don't want to go through this, right? C of theta plus phi, CC minus SS, S of theta plus phi, SC plus CS. That's what it comes down to. And that's enough to be able to remember the sum and difference formulas. The double angle comes from just letting theta equal phi in this. So for the double angle, C squared minus S squared. Or sine of the double angle, well, then SC and CS are the same, so it's 2SC. Okay. And the tangents are the same way, and it's a little bit awkward, but not that bad. Okay. Tangent, remember? Tangent is sine over cosine, yeah? And so you take your cues from the plus or minus. Tangent theta over plus phi. Sine, I see plus plus, right? So it's tan plus tan over over 1 minus tan squared. No, 1 minus tan. 1 minus tan. Yes, theta phi. Thank you. Okay. But again, so I'm going to write that here. I'm going to rewrite that again in the form that you're going to see, and it's kind of nice for you. The way students actually want to remember this is t plus t over 1 minus tt. And that's easier to write and easier to remember. And the only thing to remember is the first time you see the t, it's theta, and the second time you see the t, it's phi. And then again, the tangent of 2 theta is then just 2t over 1 minus t squared. Except I want to write that more cleanly. And so that's the way you remember them, right? But again, you can always get them again to remember which one with the cosine or the sine got the minus sign. Multiply c plus is times c plus is. Okay? Now, the most important one here of these is this one. Because that gives you the double and half angles. Okay? So the Euler identity gives you the sum and difference. Sum and difference give you double angle. Double angle on cosine gives you the double and a half. Let's do that over here again. Yeah. C2, wait. Purple. C 2 theta is cos squared minus sine squared theta, yes? And that's equal to 1 minus 2 sine squared. And it's also equal to 2 cosine squared minus 1. And that came from Pythagorean identity. Oh, hi, Jewel. Yeah. I'm running through this again just as a real fast review. I know this is stuff that we covered before and it was weeks ago. Okay? But I wanted to make we had all the basic things in at one time. But this is a review of the stuff that we did before. The basic idea here is fairly simple. Use the C plus IS to get the sum of difference formulas. You let theta equals phi to get the double angle formulas. And then you look at the three different forms of the double angle for cosine. I know the Euler identity is confusing, that's why I started it to begin with. If you don't use the Euler identity, though, then you have to memorize. And the idea behind the Euler identity is fairly simple. I think you can multiply C plus IS times C plus IS. And I know mostly you guys don't have issues with it because you just don't really have a good feeling or a comfort level with imaginary numbers. But those are very important. A lot of things in the real world work with imaginary numbers. Kind of like a lot of things in the real world work with negative numbers. It's just one of those things. And the thing to remember on all this is C plus IS times C plus IS. That takes you everywhere you want to be. The actual proof of the Euler identity is, again, something we're going to work with later, right? And I'm going to clean all this stuff up here so that we just have just the bit that we need, okay? So here's the review that we want. The Euler identity, this is the idea here, is that e to the I theta times e to the I phi is C plus IS times C plus IS. Okay? So cosine theta plus phi, CC minus SS, sine theta plus phi, SC plus CS, and that comes directly from just multiplying it out. C2 theta is C squared minus S squared, is 1 minus 2S squared, is 2C squared minus 1. Okay? That's the most important, the 2 theta on this. And that gives us that S for the half angles is going to be, now you look at the S here, look at the S here. That's going to come over 1 minus cos 2 theta over 2. And the cosine is going to be 1 plus. So that's everything. That's everything. There, these are the Euler identities. There's some difference just by placing phi with negative phi. Here is the most important of the double angles, the cosine 2 theta. And from the cosine 2 theta, we get the half angles. Okay? So these are the three most important. Sum diff. That was supposed to be green. Sum difference, double, and half. Of these, probably the most important is the half angles. These allow us to do calculus problems that we can't do without them. Okay, most important is probably the half angles. And so that's all the important Euler identities. We also want to talk about solving general triangles. This is the other thing we looked at today over the course of the last few weeks. Give or take a couple weeks off for extended spring break. Okay. Now remember the law of sines and the law of cosines, yes? The law of sines gets written in a way that you're not going to use it. Right? It gets written as, First of all, let's draw a triangle. And I don't want it to be a right triangle now. And the law of sines tells you that sine A over sine A over A is sine B over B is sine C over C. Okay? And that's the way it's written, but the whole point on this is to have these set up. Okay? The important of these is, remember, these are altitudes, right? And so you set up the standard grid of angles and the sides that are opposite them. Yeah? Right? And these crisscrosses are altitudes. And the altitudes are the same. So I get B sine A is an altitude, and A sine B is an altitude, and all these crisscrosses. And these two are equal. Okay? That was the one that we used, right? For solving using the law of sines. We had, law of sines has the ambiguous case, right? Remember the ambiguous case, guys? Okay. I'm going to clean this up a little bit. Which I'll write gently as SSA. But we all know which direction you read that, right? Yeah. Okay. And this is always the case where you have to pay attention to what was going on, right? So we had A, B, and C, the angles. And the sides A, B, and C. And we have our two sides and just one angle opposing them. So what ended up happening, we had one altitude. We had one altitude, B sine A. Altitude, B sine A, yeah? And that was the only altitude we could calculate. We know what the other altitude would have to be, but the ambiguous case we have to check. Everything else is pretty straightforward. On the law of sines and law of cosines, it's just the ambiguous case which causes issues. And so that was the one I wanted to treat during the review. And so the idea here is we have this flow chart, right? Let me zoom in and list a little bit for us, okay? So the flow chart is, first of all, let's label these a little bit so we see it, right? Remember that this is This right here is the angle A, right? Yeah, that's good. Okay. This is opposite. This is adjacent. Okay. So the flow chart on this to calculus was to first check to see if the opposite was greater than the adjacent. Okay. If the opposite was greater than the adjacent, we got one triangle. Okay. Let me draw a little bit of a sketch on this so that you can see what's happening. This is the bottom side that we don't know about. Here is where the angle is that we know. This is the only angle we know. Okay. And then we know the side that's adjacent to it up here. And then we have another side, but we don't know where it's going to swing down. This is the opposite side. Okay. Now, if the opposite is, and when this swings down, it's going to hit that bottom line two places, if it's long enough to hit that bottom side. Okay? And when it swings down, we need the opposite greater than the adjacent. If the opposite is greater than the adjacent, then we're going to get one triangle. Okay? Now, it's possible now, if that, and that's the only thing that can happen, if the opposite is greater than the adjacent. We'll get one triangle, it's not ambiguous, and everybody cheers and you just solve it. The next thing to check right there is if the angle is obtuse. Because if the angle is obtuse, if this original angle theta, my angle A here I should say, if that angle was obtuse, we'd be looking over here for my adjacent. And then if the opposite's less, you're not going to get a triangle. So after I've checked to see if the opposite is greater than the adjacent, and I know it's not, because I'm continuing my flow chart, if A is obtuse, we can't get a triangle out of this. No triangles. Okay? Now, for the next thing, if so I know I'm at 1 and 0. Now I want to check to see if we're actually at a spot. Okay? Now for this to actually work, if it's obtuse right there and it's not, the way I'll get two, it's possible for me to get two triangles if the opposite is greater than the altitude. This is the altitude. And that's the B sine A that you see here. So you'll calculate that on your grid. And if the opposite is greater than the altitude but less than the adjacent, then that's the only case where we get two triangles and you have to do the extra calculations. So if the opposite is now greater than the altitude, that's when we get two triangles. And I could just say, if none of those are in there, well, and if we fall out right there, the opposite isn't greater than the adjacent, A is not obtuse, and the opposite is not greater than the altitude, that's when we get zero triangles. And now the other calculations from that, from the homework, right, you have to remember that you get two triangles, and the triangles are, in this case, A, B, C, and A, B, C. A is not going to change, right? And the sides that were given are not going to change, okay? But we're going to have a first and a second B. Here's B. And they're going to be supplements. And then we'll get a first and a second C. And they're just going to be whatever's left over. And after that, you fill in that last missing side using the law of sines, the law of cosines, whatever you like. Okay? The only thing I want to point out here is that B1 and B2 are supplements. They add 180. I'll put that in the chart here. Okay. So I'm doing what I can to try to make this as comfortable as I can, but I know we're all changing this. Yeah, it's a little bit different, a little bit of a challenge setting this up when I can't actually, look at faces and see who's confused and who wants me to slow down, and people can't just ask questions the easy way. But there it is. Yeah, we'll do with what we can. The last thing I wanted to look at today was calculations using the dot product in the polar form. That's the last thing that we're reviewing that has to do with trig. Okay? And the reason the dot product is interesting, as far as trig is concerned, is because given two vectors v and w, we know that v dot w is the lengths of the vectors. And we know how to find the lengths of the vectors because that's just the Pythagorean theorem times the cosine of the angle between them. Just like that. Okay? Now, the real use for the dot product, and we know how to calculate the dot product, it's just easy, it's just multiply and add. The real use for it is for checking to see when things are perpendicular. If things are perpendicular, then that angle between them has to be 90 degrees, right? What's the cosine of 90 degrees, guys? You'll notice I asked this question earlier, right? What's the cosine of 90 degrees? That's right, my lady. And so the nice thing is if you're taking a dot product of two vectors which are perpendicular, because you're going to end up multiplying by the cosine of 90 degrees, the dot product is 0. And that's one of the very first most important things to remember about the dot product, is that the dot product v dot w is 0 if and only if v is perpendicular to w. Now, by rights, I should be putting little bars on top of my v's and w's. Yeah, so I know these are vectors, not just numbers. But nobody does that unless they have to. Because this is going to show up in your notes and you'll be looking at it, I'm going to put the bars on top. But I wouldn't normally write them in practice because it's just too annoying. Because I know they're vectors. But I'll put those up there so you can see them, right? Let's do one quick calculation with the dot product on this, just to make sure that you can have it, okay? Here's an example, and the example is 3, -2 for v, and w is 1, 5. Okay? Make this very simple. What's v dot w? I'll put the bars up. Okay? Somebody needs to calculate v dot w for me. What is it? v dot w, guys? Okay. You're like so close, Danny. You're so close. Yeah, you have to multiply them. That's right. Do you see Geraldo's answer? See the difference? Yeah, Geraldo's right. That's right. That's right. Because the dot product of two vectors is no longer a vector. It takes it back to scalars, right? And that's the thing that students get easily confused. There is a vector product that gives you a vector. It's called the cross product. And you will cover that eventually in calculus. But we're not, and also, yeah, in linear algebra. But yeah, this one right here, the dot product just takes you from two vectors, gets you back to a scalar. And so you take that product just as if you were, and then, yeah, you add them together. So it's 3 plus negative 10 is negative 7. That's what's happening. Yay. Okay, so there's v dot w, yeah? I want to find the angle between them, right? Now, theta, right? I'm not sure what theta is. What's theta? Well, I know the cosine of theta is, what's the cosine of theta? Oh, look, here it is. There's the cosine of theta. It's the dot product divided by the lengths. It's the dot product divided by the lengths. What's the length of v? And then what's the length of w? What's the length of v, guys? Somebody? It's the square root of what number? The length of v is the square root of what number? Anybody? Anybody? Square root of what number for v? What's the length? Everybody watching the chat, I hope. Length of what? It's the square root of what number? Anybody? How did I get 13? Yeah, how did I get 13? Look at v. How did I get 13 out of v? Would you like a hint? My hint is an ancient Greek whose name starts with P. In English, anyway. In Greek, it starts with pi. Pythagoras. Square root of 3 squared plus 2 squared. That's exactly right, Jewel. Awesome. That's where 13 came from. Add the squares. Ignore any plus or minus, because when I go ahead and I saw you write the negative 2 squared, but it needs to, and the negative 2 actually needs to be in parentheses, because it's negative 2 times negative 2. There we go. And so it's root 13. And so root W is what? What's the number, guys? What do I need to put into that radical? Anybody? Yes, Alex. Alex, awesome. You got it. And so there we go, guys. And so I've got negative, cosine of theta is -7 over, I'm going to cheat and say 13 root 2. I'm going to say 13 root 2. How did I get 13 root 2? Well, because I multiplied these two together. Root 13 times root 26 is root 13 times root 13 times root 2, or 13 root 2. That's how I got it. Yeah. So I did that probably a little faster than you, but it's okay. You could have done that too. Anyway, guys, that's a number, right? That's a number. Yeah? Okay. Hopefully everybody's got a calculator. What's theta? What's theta, guys? Actually, I've got a calculator, but I got to get up and get it. Oh, wow. So I got this like bag of calculators to hand out, and I've got like no way to hand them out. It's kind of wild. Okay. Danny says it's 112.338. Okay. The first thing I know is that it has to be over 90. Do you know how I can tell it has to be over 90? Anybody? How did I know it had to be over 90? Let me put it this way. How is it positive that it's over 90? How is it that I'm positive that it's over 90? And Geraldo, I'm not sure how you got that. I know it's over 90, and I don't know. I haven't actually tried the calculator myself. Let me check it. Our cosine in degrees of -7 divided by 13 root 2. Okay. Now let me do one little thing here, as if I didn't pay attention, and see if I can get that 91. Nope. So I'm not sure how you got the 91.19. But in either case, Danny is correct. Danny is correct. The number coming out of my calculator is 112.38, 01351. Yeah. The reason I knew it was more than 90, remember our cosine, guys. Cosine is an x thing. Positive values here, negative values here. That's how I knew it was more than 90 degrees. Yeah, oh good, I'm glad that that was great, so you got that. So you're able to fix the calculator. I really wish. And so cosine is just the arc cosine of this. Of -7 over 13 root 2. And you got to be careful when you're plugging it into your calculator. And the usual rule is you plug it in twice in case you had a typo to notice. And it comes out here as 112.38. Whoa! That shouldn't have even been possible. It's not supposed to be able to duplicate like that. This program can't do that. Anyway, but it did this time, huh? There you are. Okay. And so Alex is getting 139.59. I know how you got that number. Okay. And that was the actually number that I was looking for people to make a mistake on. Here's what you did. You plugged in arc cosine -7 divide 13 times root 2. And that's what you plugged in. The difference when you plug this in between that and what we actually want are these parentheses. Do you see that? Oh, good, you figured that out. That's great. That's great. That's the parentheses that you worked with. And that made the difference. Okay? Yeah. So anyway, guys, that's going to complete our review on trigonometry. And at this point, I'm going to stop my recording. Again, the recording is going to be up on YouTube, and it's also there on Blackboard. I'll show you how to find it on Blackboard in just a second.